Then we have Morten to...
And then there is Morten.
Let's finish the presentation session with Morten and
I need some
his
glasses.
realistic 3D for reality. Okay, realistic for reality sounds nice, and it is about immersive remote operation.
Yes, so I was thinking about when you invited me. Thank you, first of all, for inviting me.
Always
It's
welcome.
thanks to Atanas that I'm here. He paid my flight ticket. But it's not only because of that. There is a history, in fact. And I was thinking of that when I was going to come here. I said, okay, 10 years of CIVIT. What has happened in the last 10 years? This is CIVIT, but there was a beginning. And at the beginning, there was 3D ControlNet. And if you look closer, then of course you can find both Atanas and me together there. So we had a history here, but it continued. So then there was European Training Network for Full Parallax Imaging. And you can see Atanas over here, and I was a bit tired over there. And now there is still, in fact, Plenoptima. We're about to finish it off. You can see Atanas down there and me over there. So we're still there. But still, there is also Erasmus Mundus Joint Master in Imaging. So we have a common education. So also with Politecnico di Milano. And there will be, at least next year, we will have the conference. So where Atana is the big boss, and I am allowed to be the little boss here. So, sorry?
If I retire earlier, so you take care of it.
I'm not so sure. Maybe I will retire too. So anyway, that was the history in that way. Today I'm going to talk about a little bit about remote operation, which I think is a very nice application of what we've been doing here and presenting. We have heard very nice presentations from industry and then how we experience things and so on. So let me first just present a little bit about me. I'm Morten Sjöström. I come from Sweden, and we have a research group called Realistic 3D at Mid Sweden University, and I guess where you know where Sweden is. It's just across the bay over here to the other side. We have 8 research centers, of which I belong to one, and I'm heading this research group, Realistic 3D, and this is how the group looks like today. Now, there are a lot of PhD students finishing, and there are some of the adjunct professors disappearing, so next year will probably be much less. But what do we do then? We do a research on visual AI, we say today, because we use visual data and we use a lot of AI to do this. Where we look at a lot of things like imaging and visual data understanding. We look at visual data processing and compression, and immersive visual expression, and everything we found on signal processing and machine learning today. We have had a lot of projects related to remote operation. Today we're working in something called Immerse with the University of Oulu in the north part of Europe. We've also been working with the mining industry for systems for remote scaling. And we earlier also had another project called Lightfill as an enabler of multi-view surveillance and photographic VR. We have a few more as well, but it gives an idea of where our focus has been so far. So why do we look here? Well, in fact, there are a lot of activities in industry that are interested in this. And why is that? Well, you have here a remote site and you have someone steering this. And what does he need? He needs, first of all, information of the remote site, and he must be able to do some spatial judgment, say where I'm going to put the tool, and he must have sufficient quality to do so. And since he's interacting with this, it puts some time constraints here. We can't use as much time as we wish. This is why I asked Peter earlier, so how long does it take to do this model? Well, it takes 2 days. This must be in real time. It's no way we can use that model. In industry, we also have many different applications. It started back in the 1930s when they want to control the hydroelectric industry. Maybe they didn't have the visuals then, but at least they had some remote operation. And now to the renaissance of technology, there are a lot of industries that want to do this. There are airports that have remote air traffic control. Mining industry, I think, is very important because then the people don't need to be down in the mine and having the risk of having stones falling over them. And then you see there are a lot of other different industries that are interested in this. So why do they have this? Well, there are some advantages. The answer: safety and efficiency. It can actually increase inclusiveness in the sense that people that could never go down and run a big machine in the mine could now sit in a room that looks more like an office. And you can also reduce to commuter sites, meaning that the air traffic controller, he doesn't need to go to the airport. He sits hundreds of kilometers away and can still run this. There are some challenges still then, and we heard many of those today. So we are mainly looking at the visuals, and that it's about delivering visual information to the operators, but you could later on imagine to supplement that with audio or haptics or something like that to supplement that information. So what is the information? We are focusing on visuals only and not including the other parts for the time being. You start here with some kind of capture of scene. You have camera rays or depth sensors. You need to compress it and transmit it. You do some post-processing, you do view augmentation, you render it, and then you have to look at the quality of experience in the end. And Federica's very happy. There has been a lot on transmission. I mean, and I think that is kind of interesting. I think it's more the telecommunication industry that is pushing, oh, we need to have more data being transferred. And when I asked them, so how do you compress this? Well, we use this encoding H.264. Okay, that's 2 generations old. You probably have 25% of the data that you need to transfer if you use the latest. Why are you using that? And they have no clue. So I think it's very important to have an understanding of the whole processing chain in order to do the right decisions. What is not showing in this picture is actually this guy that sits over here needs to control this. So we said he has to do this in real time. So we have a time constraint. And real time depends on the situation. If you're going to be driving something like a hydraulic machinery, it's about 100 milliseconds. If you're going to be playing music together, if that is the case, then you have 3 milliseconds or maybe 10 milliseconds. So it depends so much on what you're going to be looking at. But we speak about real time because we want to somehow have a video in normal speed, so 30 frames per second or 15 frames per second. So that's what we mean with real time. So let us look at a number of specific solutions for remote operations. We have built many capture systems in our lab, putting cameras and putting computers together. Nowadays, we're mainly focusing on reusing data that others are producing so we can compare it, and we are more focusing on the processing part. So once we have the data, we want to generate different views. And why is that? Well, if we have 2 views, we see stereo, we can adjust distance. If you understand how we work as persons, if we want to see something, we look around a bit. So we want to generate several ways. And also, if you want to look around in different directions, it's useful to be able to see different views. So we want to do generate this in real time. And to do so, we do new synthesis. There are different ways of looking at this. We have explicit representation, semi-explicit and implicit representations. And in the good old days, we had depth image-based rendering. So that is what been done. And then now there is more Gaussian splatting, planoxels, light field, neural radiance field, and nowadays a lot of pause-guided diffusions. It's kind of slow, but it's interesting technology. But if you look back a little bit, we're talking about 10 years. This is more than 10 years. So we have depth image-based rendering. You know that if you have the information in depth, you can render a new view and it looks kind of good. The problem is that you get disocclusions, so there are a lot of missing information. And back in the days, what we did is that we identified the small holes that are very easy to fill. You can have larger holes, you must have more sophisticated, and you could even have translucent. You see, if you move this, you can see straight through this woman. So we realized, we have to figure out how to deal with that. And that we did by looking at different layers. We looked at models so that we had the lines in the background and so on. So it's advanced method to do this. And these are different methods that you could do this. And of course, when we come to our method, it looks very good. Back in the days. I don't think it looks so good if I look at it now and see what we can produce today, but in those days. Now today, 2D plus rendering still works. Now they use neural networks to do the same thing. You have 2D plus depth, and then you have a flow decoder, mask decoder, in-painting decoder, and this is someone else that's done, but they get kind of good results and they do it in real time, and it's definitely better than we did. There is also, if you don't have the depth maps, you can estimate the depth map, and in this one it's actually 2 images, and they do a flow estimate between them, which is more or less the disparity estimation. What is interesting here is that here they introduced features as well. The upper one is just moving the pixels like in the IBR, but here they looked at features, and they did re-rendering of the features, which is high frequency components. And then in the last stage over there, they combine that, and they can actually get a very good results. Unfortunately, this is very slow. So very good quality, but very slow. Hello? Yes? Here we are. Okay, we heard earlier today about some implicit representations, that you have some kind of continuous 3D function mapping by training either a neural network or some other representation to get this. And it's computationally very expensive and very memory heavy. So for remote operation, it's not really an option, but they are very nice results. You look at the nerve. There is also the planoxels. That is a sparse voxel grid. It's kind of faster. It didn't really hit the road, but gave similar results to the others. Gaussian splatting, and then there's something called quark as well. But it's not useful because all of them are kind of slow. Gaussian says real-time rendering, yes, but we heard it takes some time to actually create these models. So here you can see it looks very nice when you have estimated these and you run them. Now, and also neural, we have some neural radiance field. We have some examples here, so they look very well. Gaussian splatting. The original Gaussian splatting, what they do is that they have multiple images from different perspectives, and they do structure for motion to find a grid, and from this grid they train the Gaussians to get something. Now we heard from Peter today that he skipped this structure for motion, instead you use a nerve and get very good quality there. What we have done now, this is the traditional structure for motion, Gaussian splatting. You have all the Gaussians, you project those onto a view, and then you do a render regression, meaning that you take all this and you know, see how they splat onto an image. Now what we did is that we started off from something called steered mixture of experts, which is very similar. We have a lot of Gaussians, but in fact we have some experts and some soft partitioning here, which in practice is a new regression method. And the advantage here is that you get much fewer Gaussians that you have to train, which makes it faster to train and faster to render. And this soft partitioning makes it also very sharp transitions between. The Gaussians can never be so sharp, but in this way of doing it, you have very sharp transitions as well. So we have extremely good quality.
Now we dive into visual comparisons. We begin with the low BPP regime. Compared to 3DGS, our method achieves better visual fidelity.
You can switch off the sound, I speak instead.
3DGS
So you see to the right there, you have the quality that we managed to do, and this on the other side, and you see that the PSNR are much higher. We still have the number of Gaussians. We have fewer than they had. So this is actually something we're going to present next month in December at SIGGRAPH Asia. And if people are smart, they will use this later instead of Gaussian splatting because it's smaller, quicker, and more accurate. Now, it's still not practical for the remote operation system. Then we can think about, okay, if you had the multi-camera rig, we have a lot of dense light field like this, and then we can render a view from this. So it's just interpolation very quickly, very fast. So the last step there, called light field rendering, is extremely quick. So if you have multiple cameras, you can do this, but that, of course, is very unpractical. It's about calibration, it's about having a lot of equipment synchronized and so on. So we got the idea, why don't we just take one image? Can we from one image render the light field? Meaning that we take one image and then we kind of produce all the other images around. In fact, we can. So what we did is that had been done before, but we wanted to have a 360 camera because then we can look around. And we wanted to able not only to look around in 3 degrees of freedom, but we want to be able to move around as well like this, because then we have full motion parallax. So what we did is that we took the ODI and we reformed it into a cube, because we wanted to have a cube, then we have linear reprojection, which is easier to train in a neural network. And then we produce many cubes that, and then we realize, okay, at the borders of the cube, it's very difficult to get good quality. So then we had a refinement network that just looked at the borders of the cubes, which you see, if you unfold this again, this is what you see there. And we got, again, a spherical light field. And this we do in real time. It's kind of fantastic that we can do this in real time, I think. And the trick is that we have a small neural network. It's a unit, more or less. You could see that if the orange one here refines the whole thing, and you have skip connections to the decoder. And in order to have a higher sharpness, we use the pre-trained ResNet feature extractor. So you remember before I said there was this Shi who did a specific path where he extracted features. So we introduced that as well, and then we could render this. And this we did with, I cannot remember exact, but about 30 frames per second. So what we did, we managed to do this. We rendered the light field, and then from the light field we could do the final image. So we started to think, why do we need to do all these images? Couldn't we just go straight over here? I mean, what's the problem if we can render all those? Can't we just take any in between? That wasn't that easy, actually. The neural network didn't get it. It was easier to learn a number of fixed positions. So we had to think why. So we reused this rendering network. That's what we had before. And then we say, okay, we need to tell the position, so the target location. If you know NERF, you know that there they have to tell the position with harmonics, spherical harmonics, in order to have more information to the neural network. So we tried different representations, got okay, but we say, why should we guess? Why don't we ask the neural network to train for it? So we trained the neural network here to give us a positional representation. We combine it here, and we got very good results. So I have to press once more. So this is what we get from one image only. So I think that's kind of okay. It's not so much motion, but at least a little. Hello. Hello. No, it doesn't work. No. Okay. So we also start to look into if you saw that the correspondence in motion wasn't quite correct. So we thought, okay, can we do it in another way? So we start to look into alternatives, and then there's something called multiplane image representation. So if you have a representation of a scene in multiple images like this, then it's extremely quick to render different directions here. Now, if you have 2D plus depth, you can do this kind of well. There are very good neural networks that do that, but we only wanted one image in order to save transmission capacity. So we tried. We wanted to have a single input image, a neural network producing the multiplane, and then it's very quick to render the novel views here. There are very good such neural networks, but again, very slow. So we wanted to do something quick. And we didn't reinvent everything from the beginning. We took the scene encoder as we had before. This we had done, so we didn't do it. So we instead trained a density decoder in order to get the alpha values of this MPI, and we also took the color decoder to get the colors for each plane, and we got very good results. But I thought, can we do it even better? Yes, if we know the depth here, maybe we can train with respect to the depth. So we actually entered a new depth decoder here as well, because this representation that you get in layer n, it's a representation of the whole scene, what you see. So that should contain depth as well, because we can render all these different layers, which is depth. So we introduced a depth decoder, and we didn't really have the depth here, so we do the pseudo ground truth by running a very good neural network, and we did this, and we got even better results then. And I think this is here. This is depth map we got, and then this is how it looks like then. It might, Federica, do you see the difference? No, it's difficult to see this, but still, it's a fairly. If I have medium sized with 30 frames per second, larger images than with 15 frames per second. So the others are not even close. They are maybe 3 frames per second at the most. Within remote operation, we also believe that we have digitized the information. We're taking a picture, and it's digital. Why don't we use that to actually extract information? That's what we're doing when we're rendering, but you could do that also to identify objects and support the operator in different ways. So before, a couple of years ago, we tried this by introducing overlaid graphics. And you can see we had a digger that we were supposed to drive a little bit in our lab. And we then just introduced saying, oh, this is where you are, this is where you should. That was helping a little bit. And then we put the grid, and it was very easy to see that the 2 dots followed and came closer. And we also put vectors to see, okay, it's in this direction, you should go that direction, a little bit down. Nobody understood this. So a very simple conclusion is that you need the correct information. It should be rightly put. We by accident put one graphics over there, so they have to look on the side all the time. So that of course didn't work, and it didn't work when you put something in the way either. So those are design things you have to think about. And as I said, it must be in the appropriate form as well. And these are just simple things that we have done. We have tried some other augmentations, not overlaid, but in this center you can see that we have filtered out the robot, so you could see behind the robot. And that is possible because we have cameras from each side. We also try to do extended views, but then there are so much disocclusions that we didn't render in those times. So that was not so good. Now I said that it has to be compressed, a lot of data into a very narrow transmission channel. So we have been looking into how we can code this visual data, and mainly we've been looking into light field because that's a lot of data. It's maybe outdated in the sense that we don't need that many cameras, but at the days we started to have all these cameras, and then we just made a pseudo sequence of that one, and we did this, and it was back in 2006. That's more than 10 years ago. It's 20 years ago soon. So we said, okay, there are better things. Why don't we put a neural network to do this? And of course, we got much better results. Then we start to think a little bit more and say, okay, the distribution of information within an image and between images are different. So why should we use the same encoder for that? It's like the prediction between frames or within the frame. So we subdivided the information of the light field in spatial domain and in angular domain, and then we encoded them differently. And we got the latent space that was spatial features and angular features. Then you entering, you do some entropy encoding, transfer it, entropy decoding, and then we have on the receiver side, we have a neural network to reconstruct the image. And it works very well. And in fact, by separating this, we were very efficient in compressing. And then we said, okay, can we do it even better? Yeah, we can do that. There is no pointer on this one. You see in the middle, that's where I have the angular. Sorry, there is a pointer? No. IT nach Hause telefonieren. Angular latent space here in the middle, that's what you recognize. And then we said, okay, if we know the distribution of that spatial latent space, we can have a better entropy encoder. So we have the hyperspatial latent. So we have another neural network up there that finds out the distribution, which originally it's assumed to be Gaussian, but it's not. But finding out that, we can help the entropy encoder to be a better entropy encoder by telling it, okay, the distribution is like this. And the same thing for the hyperangular latent. So we got some very good. What we also did is that at the very end, we wanted to make sure that the latent and angular spaces were separated. So we put an extra cost function to separate those two to be spatial and latent spaces. So we got very, very efficient compression. This is being published now in Federica's journal. It will appear soon. So this is really latest research. We also believe, I believe, that neural networks are too big in general. You have millions of parameters, and why should you have millions of parameters when you represent a system that has a degree of freedom that is much, much lower? And you know from linear algebra, you just need as many parameters as there are linear equations. So there is a little bit more complex of these processes, but in generally, why should you use so many parameters? So I wanted to compress it, and I told my PhD student, okay, how can we do that? Pruning is kind of common, quantization is common, so we instead looked into convolutions. And we saw that there are a lot of convolutional blocks that are repeated. So what if we can make those more efficient? So we tried different convolutional blocks that exist. We just tested, and we can actually compress it very much. And then we thought, okay, there are advantages to have large kernels in the filtering and within a convolution, or smaller. Well, larger, you have a more receptive field, smaller are faster. So which one should we use? Well, then there were some people that realized if we, within such convolutional block, let some convolutions be 3 by 3, and some 5 by 5, and some 7 by 7, up to 9 by 9. And then we just combine them at the end, and we take what's best. What they did is that when they separated into the different, is that they kind of said, okay, you go there, you go there, you go there, of the data, and didn't think more than that. And we said, why shall we, as engineers, as researchers, say what data should go where? Why don't we let the neural network do that? So we introduced here the depth-wise convolutions. There is 1 times 1 here, to actually let the neural network learn itself which part should have large kernels and which one should have small kernels. And by doing so, we were even more effective. Let's see. If we look at this, the EpiNet was the original neural network that we started with. It's estimating depth maps from a light field. And it has like 5 million parameters. And we moved it down to 1.4 million parameters. And the funny thing, we even improved the quality. You see, it reduced the mean square error. So just by thinking a little bit, we could reduce the size of the neural network quite a lot. And why is that important? Yeah, because then we don't need a very large computational device, maybe at the remote site or when receiving. We're saving energy simply. Now, this was a lot of engineering work in the things, well, we had to think, how shall it be done? Can we let someone else do it for us? And then there are neural architecture search. And if you look at darts or where you can differentiate this, you let an optimization routine look at different possible solutions and solve that. So we have looked into different ways of doing this more effective in the actual optimization. Okay. Everything should be open access. So if you want, you can go into our webpage and you can download code, papers, anything you want. You can take the QR code and you search on my name, you will find it. And that's all, folks. Thank you.
Thank you. You managed to present 61 slides in 40 plus minutes. So now it's time to explain some of them, so questions?
I mean, I could have presented even more. We have Erwan up here who's also working with us. He's optimizing how you should distribute the computation into GPUs. And we also have another PhD student looking into how should you do, how you fill the seclusions by looking into inverse problems. So I can speak another 20 minutes if you want.
We have some open wine outside.
Okay.
Maybe we still have questions, time for questions.
Robert. I hear you.
No, you will
Depends
get
if
a
they're
mic,
recording.
don't shout.
Now, your talk was kind of focusing on immersive remote operations.
Sorry, Eve?
Your talk was focusing on immersive remote operations. This is what you said as an application use case.
Yeah.
But then you're also saying you are kind of promoting that we should have only one photo and we should let the neural network decide how the environment looks like. What about safety?
Oh, yes.
Are you happy about the hallucinations of the
industry
network?
says, forget about this, because... No, there's a good point. I didn't want to mention that. The problem is that the industry, when they do something, they remotely operate a a robot, they need to know if they move their head and they want to look behind. It shouldn't be hallucinated information, but must be the true information. And Peter mentioned that they actually made some information saying in a different color to say, okay, we don't see behind here, so we just keep it as it is instead of trying to hallucinate something. So a very good point. You must somehow tell that this is hallucinated information if you move around. So maybe one image is not the best, maybe one should have two and you only interpolate. It is not fully covering all the angles, but it will improve.
Yeah, more questions?
Fredrik.
Yeah, thank you, Martin, for this very illustrative talk. So at the end, you mentioned you want to bring down the number of parameters of your model. So maybe then I should not ask this question, but what if you... yeah, but, exactly. So you have shown many architecture slides about CNNs. What if you would try it out with vision transformers or transformers?
Yes, we're looking into that. And the guy that's been looking at the reduction using CNNs, I told him, can we do a visual transformer killer? Maybe, he said. So we're looking into that. We don't have a solution to that. But it's true there you have extremely many parameters they need to train. And why don't you do that in CNN? It's because when you do it in CNN, you need a very deep CNN, and then you have problems when you train these because the gradient explodes and there is too much simpler. So yes, we're working on that. So in 10 years, I'll tell you when I come back.
Okay, thanks.
We heard wine and nobody wants to ask any more questions.
Yeah, we're still good in
time. Two more minutes.
Yeah, I was thinking of, more questions. I was thinking of formulating my question. Robert almost asked the same. So like, it's probably important to quantify the limits of single image light field reconstruction, because this light field is very so you are showing like going around, but you are not showing a wide baseline and these things. And in work machines and AR applications, this is it might be important.
Yeah, no, you're definitely right. What we have done in the last one is to have a cube of 20 times 20 centimeters in which you can move around. So which is as much you can do if you sit in a chair and you look around. You don't move the head more than 20 times 20 and even 20 forward, backward. So that's the limit we have today. But as Robert pointed out as well, we hallucinate information, and that's not allowed in industry because they really need to know. So we're looking into new ideas that I will tell you about in 10 years.
Okay, yeah. So multi-camera is not dead. Yeah.
I don't think multi-camera is dead. I think smart multi-camera is winning in the end.
Okay.
One more minute.
No more questions. Take Morten at the interactive session, networking session, and ask him more questions. He can tell you more things.
I hope so. Yeah. So let's go and have some wine.
Right, some logistics. So we go to the lab now. For those who don't know where CIVIT is, you go either, you have to be at the second floor. So either go this door, or if you go here, have to take stairs and go upstairs. And then you cross the restaurant, you take the corridor toward the buildings, and then you turn right. And then when you turn right, you will kind of see where CIVIT is. There will be posters and some other signs. So just go outside, right to this direction, then again right after the corridor, and we'll meet there. You can take this leaflet. It describes the demos that we want to show and where they are placed inside the rooms. So they will be there around where the food is served and also the entrance to CIVIT is. Okay, let's go there. Thank you.